Yes, good morning and welcome to my first video in 2025. I'm going to be looking at applying Newton's second law to explain weightlessness, right? The weightlessness as a concept is not clearly covered it's not well emphasized in the IEB, ISC syllabus. But Newton's second law is dealt with thoroughly. And also the concept of free fall. Learners are expected to know what free fall is. And they do a lot when you do vertical projectile motion, the objects will be under free fall. And sometimes when the objects are falling on a frictionless surface also, it would be free fall. If the only force acting on it is gravity. Okay, so, right. Newton's second law, formula-wise, is F net is equals to MA. That's the first thing that we need to know. Then the next thing I want to explain is the concept of weight. Weight is always directed towards the center of the earth, and it is FG, right? Over here, I tried to draw a situation of a lift, right? Which I want to use the three case examples of lift going up or down or being stationary to explain the concept of weightlessness. But before I go into that, I want imagine this is a glass bottle, and if I make a hole somewhere near the bottom there, what happens? The water will come out because the water has pressure, right? The IGCSE guys, you know that pressure is equal to rho, the density, times the acceleration due to gravity, times the height or the depth, right? The deeper, the higher the pressure. Okay, you know that. But the concept of pressure, actually, if you do the derivation of the formula, you'll see that it comes, without going a lot into fluid mechanics, it is derived from weight, right? Because pressure is force over area, force by area. So you calculate the weight first and divided by the area. Okay. So I hope we are all on the same page on that. Good. Now, the other thing that I want to explain is when you measure your weight on a scale, for example, the scale is not measuring the force going towards the center of the earth. It's not measuring the gravitational force, right? Remember, there's two forces which are balanced when you sit just standing. Gravitational force and normal force. So they are normally, this is normal force. I tried to draw it beforehand, but it may not be very clear there. Normal force, the two forces, gravitational force down, the main is in the lift, and the normal force is that one, right? So the water example I was giving is the water comes out, right? But if you release it and the bottle now is under free fall, you can do that experiment at home. Very nice experiment. No one is going to be injured. Just the plastic, put water in a plastic bottle, right? The moment it's under free fall, you will see that the water is not coming. If you can't see the water properly, color the water with a food coloring so it's not poisonous. Okay. Then you will see that the water won't be coming out when it's in free fall. So its weight is going to zero. Okay, we'll explain how that happens. Thank you. That's the purpose of this video. Right. So case one with the lift. The lift is stationary. I wrote the word stationary there, not very clear. Or it's moving with constant velocity. Stationary, constant velocity. I'm sure you get, right? Even if it's not clear, I think you can hear me the word, right? You know that if you apply Newton's first law, this is directly Newton's first law when net force is zero, right? Okay. So the net force is zero because the acceleration is zero when the lift is not moving. It's not accelerating. When it's moving with constant velocity, also the acceleration is zero. So the net force will be zero. Now we are only going to consider the water. In this case, we only consider the guy inside the lift, and there are only two forces. How is the net force there? It's only possible if normal force is equal to the gravitational, is to the weight. So this one is equal to the weight, the normal force. So your apparent, the normal force actually, we can call it apparent weight because that is the weight which will depend on the acceleration on different situations. It can change. What is not changing is your weight. Although, yeah, I mean, if you're on the same under the influence of say, the same G, your weight is not changing. Okay. So apparent weight will change. But in this case, case number one, the normal force is equal to the gravitational force because acceleration is there. Because if you say Fn minus Fg or Fg minus Fn, you get zero if they're equal. Okay, this is right. You can't talk of weightlessness. If your feet, weight is what you feel on your feet. If you feel your real weight, your apparent weight and your real weight are the same, then you can't talk of weightlessness. Now, second case, this one, is when the lift now is accelerating downwards, right? The acceleration of the lift is also equal to the acceleration of the guy inside. Remember, we were only considering the guy inside the lift. So in this case, if the guy is accelerating downwards, it means the gravitational force, his weight, real weight, is bigger than the normal force. It's bigger than the apparent weight. So you say Fg is greater than the normal force. Then your net force, you can just say Fg minus Fn to get your net force, because this one is bigger, equals to mass times acceleration. If you make we are trying to make Fn the subject of the formula there, I put it on the right hand side. So, and then I later put it on the left hand side. You'll see that Fn is equal to gravitational force minus ma. And the gravitational force is mg if you want to start to use it. So then mg minus ma would be your normal force, which then factorizes to m into g minus a. Right. Now imagine a situation where the lift snaps and then what happens? The lift is now under free fall, and the acceleration of the lift will be g and not a. So if that happens, the acceleration of the guy will be g also. So if you substitute that a with g minus g is zero, the normal force is zero. And at that point, the guy feels no weight. He's actually weight. That's the situation of weight, complete weightlessness. Right. I hope that helps to explain. So this scenario also happens in the people, astronauts, right? In space. Remember, a spacecraft is like an artificial satellite. It has got horizontal motion, but it has centripetal. There's a centripetal force on it. That's why it can orbit in a circular motion around the planet, right? Like just like the moon, right? So the guys inside the spacecraft, I'm sure you've seen pictures of guys floating, appearing like they're floating. This is because of the situation of weightlessness. So there's also centripetal force and therefore centripetal acceleration. But I think that the Cambridge syllabus covers that bit in a bit more detail. Good. So the third case, I don't want to do it here. Case 3 is when the lift is accelerating upwards. So if it's accelerating upwards, it will mean Fn is bigger than Fg. Fn will be greater than Fg. I hope you will be able to derive the equation. And you say the net force will be Fn minus Fg. You swap this one equals Ma, and then you find that the normal force will be Mg plus instead of Mg minus Ma. It will be Mg plus Ma. Okay, which means when you are going up, the lift is pushing against your feet, so you feel bigger weight. Your weight is actually getting bigger, so your apparent weight is increasing. Thank you so much. Please press the subscribe button, share, because I would like to us to do a lot of questions, because to understand this subject better, we have to practice a lot of questions. Okay, good day.